Hello, good morning, good evening. Thanks, Christian, for the introduction. I would like to speak to you about model-driven analytics engineering, as we are trying to implement the analytics engineering approach from DBT Labs with ELT transformation on the data pipelines and also adding the data model into the DAG. And yeah, for today, I wanted to just introduce how we think about this and how we implement it, and of course, especially also what we think the benefits are. And yeah, and to fill up the slot to the end, I would hope for some feedback and questions as to whether you think this is a good idea, whether you think this is something that your data pipelines or in your head, your ideas about data pipelines could benefit from. And then I would like to start with my presentation. So for all of those that are not so familiar with analytics engineering and the modern data stack, that's like the implementation method that started 2012 with the rise of the cloud-based data warehouse databases. The first one, namely being Redshift, where we started to implement the relational model database management systems in the cloud as cloud services with also processing the SQL queries in clusters that are expandable, like the cloud promises. As you can see, Redshift is not on this slide for some reason, because we think that other tools have overtaken Redshift if it comes to functionality, but that's just a minor detail and an opinion of ours. What we do see is that with the start of DBT in 2016 as one of the very popular implementation methods for these modern data stack data warehouses, is that we have different platforms, Google BigQuery, Snowflake, Exasol, that are able to work with this ELT, so extract load transform method, where you first have like fully automated import of data into the data warehouse, into the cloud storage, and then on top of that, you do the transformations with the SQL language and with the relational model to, yeah, basically have a low code platform for your transformations as well. And what DBT adds on top of these data platforms is metadata added to the SQL transformations by using templating language. And as of recently, last year, also adding metrics definitions so that the BI front ends also can benefit from already existing transformation logic that's additionally enhanced next to the documentation by metrics definitions, so that the SQL generation can be even more automated and the handover between the data transformation and the BI front ends can also be automated. Also, what is very important if it comes to these DBT pipelines is that the metadata that's being created is not only the famous DAG, where you have the dependencies of the transformations, so that you have visibility into how your transformations depend on each other, and you can actually fine-grain control the execution of these transformations and dependency management of those. You also can add documentation and metadata that can be imported into data catalogs, so that these transformations and also the final results, of course, for the BI usage can be documented and described as the analysts would see the data. And then they can reuse these transformations for their different requirements and data products. Also, one of the reasons why we jumped onto this DBT train like 5 years ago was that there are software best practices applied. So the documentation, the transformation rules, everything is being integrated into Git. And therefore you have an analytics code base that can be also versioned and tested. And you have continuous integration processes that can, on top of those transformation definitions, make your data products more manageable and also more durable, because you're actually testing and automatically testing and regression testing your data transformations, which is, I think, a very important aspect. Also, when it comes to the different data platforms that we see here, like Snowflake, Google BigQuery, and Databricks and Exasol. So Databricks is a very, very recent addition to the modern data stack as of the DBT point of view, because they only last year integrated this after having already Spark integrated. So Databricks, in contrast to the others, is a first citizen Spark cluster, and then on top of that sits the SQL engine that makes the DBT integration possible. But also, as of last year, DBT integrates a second language. So for your data transformations in the same deck, you can have SQL and also Python in the mix of transformation logic. So you can also better integrate not only with Databricks and Spark, but also with the Snowflake, Snowpark, or Google BigQuery. All try to integrate both of these languages for their transformation code, just to make sure that we can integrate these different requirements for data science, which are mostly Python-based, and BI and business intelligence, which are mostly SQL-based. And by combining these transformation rules into one data platform, we can actually make sure that our reusage of interpretations of our data is being shared among more people. Because what we see until now, or as of recently, is still that the data science teams and the BI data engineering teams are rarely working together on the same platform because of the clash in transformation language logic they're using. And I think this is a big potential for integrating these teams and therefore reuse these transformation logics to have more conformed and harmonized interpretation of your source data, which can be reused among all use cases, regardless of the data product is using machine learning or BI reporting language via SQL. And DBT could be like the metadata language, the metadata system that combines these things. And as long as you're using the template engine to make your SQL reusable among those platforms, and the Python is compatible on all platforms anyhow, you can make sure that you're more independent of the vendors, and switching between vendors becomes, hopefully, finally, which we're waiting for decades right now, perhaps more of a reality than ever before. That's at least what I think could be envisioned by DBT and using DBT, and these platforms from the functionality getting more and more the same, basically. So, yeah. With this as background for the modern data stack and where we're at with the DBT and the platforms, and the software best practices applied, I think one other aspect of DBT and data science and the more traditional data modeling is that we have different terminology even when we speak about data modeling or data processing. And there's different kinds of data modeling terminology that are typical for the different kinds of processes and processing and data product requirements. So there's the traditional data schema modeling where we have the focal point data vault, star schema, and all the different physical schema implementations that are being developed since a long time. Also, the data value modeling, where we look into the statistics about values in the attributes, which is also a big part of the model training and feature engineering that we're doing in the data science world for the predictive requirements and prescriptive applications. And then we have data process modeling, where we have the transformation steps, where also the DBT community talks about data models, because the SQL or the Python transformation steps are also being mentioned and referred to as data models, which at the end of the day are similar to what we do with, for example, schema modeling. But it's at the end of the day, the different transformation steps, which in the final definition, in the final schema that's being accessed by the data products or BI front ends, maybe a star schema or a flat table or whatever is implemented in the relational database schema. But it's not like the actual approach of the original data schema modeling, where we try to analyze the data requirements in conjunction with the business processes. And this is the site that I was copying from Wikipedia here. And I think this is one data modeling aspect that's very much missing nowadays, because the physical implementation of the data processes and the physical implementation of feature engineering and model training and the physical implementation of star schemas to support BI front ends, it's all a very physical approach where we have technical methods and technical ideas to implement data physically and analyze data physically, but it's mostly or very far disconnected from the original idea, where we talk about what are the business requirements and actually the usage patterns that we have at the end of the day in the data products. Because regardless of what physical implementation we do, whether it's data science or data engineering or you name it, the original idea is still that we want to have our business users, the end users of our data products, to be able to measure their business processes. And if we lose ourselves in too many details of the technical implementation of the different modelings and physical implementations of the schemas or the features and models that we try to implement, then we're getting into too much technical detail, and also tend to implement technical debt too much. That's a bit of a danger that I see. And that's one reason why I think it's a good idea to rethink this current data pipelines. So typically what we have is we have multiple sources that get imported here in the green steps or bubbles, or let's say tables, or whatever it is. In the end, it could be files. Just the one-on-one representation of the source, which is fully automated, and we can import it with many tools that are available on the market, even with additional historization and persistent staging areas and what have you. But it's all fully automated. No code tools are available, and we are not really much thinking about that anymore. So that's the green level after the sources. And then we have the data products from the right that determine the requirements, what needs to be measured, what needs to be improved in our business processes. And they are accessing the data as it is at the end of the data pipeline. So once the transformation steps have been executed. And this way, we have a network of physical implementations of these transformation steps, which are not only very intransparent to business users because they're driven by technical by technical requirements, but they're also very prone to changes in the source system. So if I change something in the source system here, then the impact can go downstream all the way to the data product. And since we try to enforce reusage, then of course the data products will have will be impacted multiply by changes in one source system. And also, if the transformation steps in this network of transformations that we're looking at in a technical DAG, I think that reusage is actually being prevented because it's too low level to be discovered. So one general idea of the data product is to have discoverability, self-service BI applications. But if the underlying data that needs to be read for the analysis is driven by technical decisions, then it's not easy to make reuse because everybody in the data product in the domain area does its own interpretations of the source data, and they don't even see or realize that there's somebody else in the organization that already has done this interpretation and that could be reused just because it's not transparent. And this leads me to the final statement for this slide, that it's great that we have software principles implemented like continuous integration, automated testing, regression tests. But what is missing in this pipeline DAG implementation, from my point of view, is abstraction, separation concerns, and information hiding. Yeah. And that's what I wanted to visualize in the next few slides, what I mean by that. So first of all, in order to have a representation of the data requirements that are connected to the business processes and to the domain knowledge of the different data products, what we are usually suggesting is the ensemble logical model, which is a logical representation of the common language with core business concepts and natural business relationships that can be easily translated into different physical schemas. But this is like a traditional logical of conceptual model approach, but adapted for the current times in order to be more agile and more easily understood by the business people, because we're concentrating on non-technical terms, non-technical workshops. That's hence the definitions of core business concept and natural business relationships that make up the ensemble. So for those familiar with Data Vault, the hub and its satellites, plus the combinations with other hubs where they're linked in natural business relationships, make up one ensemble. And that's like the representation on this logical level that we would like to be driven by the business users, by the business requirements, according to the business processes, so that we have a common language that's being defined and prepared for implementation before we do the physical implementation, so that we have all the ontologies and all the definitions of the business terms, what we used to be doing with conceptual modeling, in one set of artifacts that can be understood and maintained and also created by the end users and not by the IT. And therefore, we have this approach. And this way, we would like to separate the logic that's being driven by the source systems and the ingestion, which is the data consolidation, and the view that the data products have about the data for the data derivation and discovery. So that by accessing the data, not through the physical implementation, but through logical definitions that sit on top of this, I think we achieve the first idea of the software development principles, which is information hiding, by having an interface layer to hide details of the physical implementation, because the data products that want to derive definitions and discover data patterns or reuse existing interpretations for data patterns, as I mentioned before, they are not interested in hub links and satellites and how to join them and how to make sure that the correct timeline is being hit. They just want to access business domain-driven interpretations of these data elements, which are being organized by the logical model, and then it is hidden how this joins in the background are being done. Whether there are 10 or 100 joins doesn't matter anymore, because you look into the ensemble where you have the a business definition of a customer, the business definition of a sale, the business definition of a product, a production line, and that's what you're accessing. And behind the scenes, in the physical implementation, you can even change versions of the physical model or versions of the implementation details without the data products even noticing. And that's the goal of the information hiding. And of course, by doing this information hiding, it's much easier to reuse parts of this data model, because the definitions are known by the business, by the domain expert, being created by the domain experts. And therefore, not everybody has to go back to the sources and try to understand how the operational systems implement the different concepts in physical tables, because that's the big problem that causes headaches, at least as of my knowledge so far. I mean, there are source systems, of course, that are easier, but then again, what if source systems change? So it's not only about making them easier accessible by logical definitions, but also hiding from changes of these upstream sources. So in our implementation of this business model, we're using different tools, implementations, in this case, data vault automations that enable us to automate the build in the middle, so that we don't introduce additional manual processing of the data. The only manual step that needs to be done is to map the source that's being imported via so-called hard rules into the data vault definitions, so into the logical model of the data product owners, so that we can automatically, and that's why I think of it as model-driven, that we automatically first have the logical model that's being implemented in the data vault automation, and they enable us also to build incrementally, which is a big part of this whole concept. Because independent data products that have independent domain teams, in brackets data mesh, that implement their stuff, they don't want to be waiting for each other. And that's why you have to have incremental build in place and also automate this. Not only the DBT DAG, but also the data vault automation needs to be um, automated and integrated continuously so that you can grow your model seamlessly by adding these business definitions on top. And for defining the business definitions, we're also experimenting with the data spot. And there's an interesting webcast that I know of, Remco has done with Ellie to implement Elm in Ellie, which we find is very interesting because then you have metadata that can be directly imported into the data vault automation. But this is actually still, yeah, a progress. So there's no fully automated situation there yet, but it's getting there. So we're very excited to see what's going to happen with these integrations. I'm also aware of some other data spot integrations that are being done for data vault automations, but this is just here for our example, what we used to use. And then what you have in addition to the implementation in Blue, that's what's being done by the data vault automation. These are the data vault ensembles that are being implemented in hub links and satellites. And then what we think is a very important step in between for the information hiding are the yellow entities here, because these then are the views, the ensemble views that resemble the L model from the physical tables, so that you don't have to know how to join within the data vault, or you may have a focal point or some other physical information of ensembles. But the important message is that these yellow entities are one-on-one representations, usually views, of the ensemble. So we include all the satellite attributes per CBC and all the hash keys. This ensemble is included in links, so the natural business relationships, so that the data products, when they want to access data, they only need to know what is my ensemble, what's the CBC that I want to get data from, and then they see all the data, and through the hash keys, they have the access through the links to the other ensembles, so they can link together, back together the ensembles using the hash keys or other implementation of Soulgate keys, doesn't matter, that link into the physical model, because then you make sure that you use or you can use the physical implementation for your advantage for the joining, because then you don't have any two different opinions about how to join these things in the data vault or the physical implementation. And therefore, the data products only depend on what you define in your ensemble logical model, and they do not depend directly on what the source model delivers. And then you have your final representations, additional transformations that could also be reused. And therefore, you get easier and more maintainable transformations that are lying here close to the data products, which are that then not only easier to maintain because they are relying on business logic, but they are also easier to reuse because you have fewer of them with time, and you can reuse them easier because you see the dependency from the transformations back into the logical model. And yeah, with this, we can conclude. Oh, I'm going the wrong direction. I was wondering what's happening here. So with this, we conclude the separation of concerns. In addition to this, we have the hard rules that are before the data vault, which just implement the persistent staging or data lake abstractions or whatever you need in order to get the data to be consumable by your data vault automation. And then within the data vault automation, you only need to map the sources to the target objects, which are the ensemble logical model objects. And then you gain data warehouse automation, which gives you data integration. You can add multiple sources to the same concept, automatic historization, and you have model-driven implementation, which means you can incrementally implement your data warehouse, which is very important because a lot of companies that we meet have already something in place, of course. And they're always afraid to implement new stuff because then they have to redo everything, which is not true. You can do it incrementally, and you can also have side by side, slowly changing, so to say, integration where you start with a simple one concept, one use case, and then you can slowly add the others. And you don't have to do any big bang kind of scenario. And then, of course, if you have these parts of the data integration and the historization automated, you don't care about those anymore. You don't have to think about those anymore. All implementation for the data vault or some other automation that's being used here in the middle could be other methods. They do all the patterns that need to be implemented, and they have the metadata and the knowledge for the continuous integration to allow for incremental deployment. That's very important because that's usually where the build or buy question becomes a bit complicated. And for now, I'm a bit biased here because I think the danger, even though the data vault patterns are simple, and that's how they're being sold. They're so simple that everybody can implement themselves, but it's not about the patterns. It's not about the SQL that's easy to build a hub, a link, or a satellite. It's about all the surrounding features that these automation tools deliver, which are putting in the metadata, the mapping from the source to the target, and how to incrementally deploy and build this in your continuous integration. That's where these tools should shine and should deliver the added value. And therefore, because these more complicated or pattern-based easy integration, I mean, it's also because they're patterns and they have this network idea that they grow by time. Of course, there's going to be a lot of physical tables, but that's another reason why you do need automation, right? So without automation, you cannot do any of these methods. But then with data integration and historization in place, you have your data warehouse automation, all your soft rules, the domain data product, domain specific implementations, may it be in SQL or Python, they do not need to know or implement any of those because it's already been done by the data warehouse automation. All you need to do is you can concentrate on your logic for your specific business processes. And that's why you have to have from our point of view, need to have this logical model, this abstraction in place in order to have the separation of concerns. You have data consolidation, which is only one-on-one automation. And then from the other side, you have the corresponding soft rules that can be implemented on top of this logical model. Yeah. What we suggest, what we propose, what our data stack is made of is DBT and Data Vault together. We would propose to always build the business model first, to have requirements, to have a proper software engineering approach to plan what you want to do, but in an incremental and business-driven way, together with the end users. And the physical implementation gets automated more and more. The data vault gets automated, dbt implements the schema automatically. What you gain from this is information hiding, so data derivations. When you build your data products, they are isolated from changes of the source systems, and you have easier transformation steps because the sourcing and the integration and historization has been done already, and you have the separation of concerns, so less complex transformation steps, and the information and knowledge can be actually reused because you have a common idea of what a customer is, what a product is, what a sale is, and then you can build your data products on top of that.